Alright guys, here we are again. Hopefully this last time I have to do this via video. So hopefully I'll be back next week. Alright, so this is what we left off with last time. We did that example. And now this time we're going to cover the material we need for your first project. And this is going to cover orbit determination from observations. So observations meaning position, velocity. That's what we're going to use. In other cases, you could use angular observations. There's different things you could use, but we're going to stick with position and velocity because those are the basic ones. All right, so to do this, first thing we need to do, we need to cover a few coordinate systems that we haven't talked about yet. So these are going to be coordinate systems that are basic ones used in orbital mechanics. Let's see, let's start with... First, let's start with something called the ecliptic plane. So this isn't actually a coordinate system, but we need to know what it is. All right, so the ecliptic plane, that's what it looks like. So this is basically going to be the plane which contains, this is a W here, the Earth's orbit. Around the sun. All right. So we've got basically an elliptical orbit going around, and think about the plane that that orbit is in. That's the ecliptic plane. Okay. So now let's draw this picture right here. So this is going to be a picture of the Earth. It's supposed to be kind of circular. So let's say this is the North Pole. This right here will be the South Pole. And if we've got this dashed line right here, let's say the sun's over here, this dashed line is going to represent the ecliptic plane. Okay. So this would be the plane that the Earth orbits on. Okay. So now we're going to also have something called the Equatorial Plane. So you might be able to guess what that is. So let's draw a line like this. This is going to be a line that basically represents the equator. Right. So midpoint between North Pole and South Pole, we have the equator. This angle right here, because obviously this is rotated up, this is 23.5 degrees. So this will be the equatorial plane right here. Okay. So if you hear me mention ecliptic plane and equatorial plane, that's what I'm talking about. All right. So now let's look at the geocentric equatorial coordinate system. So let's draw this picture. So let's draw this. It's supposed to be like a sphere here. So put dots here, make it look more like a sphere, and then we're going to have X, Y, and Z. Okay. So we got capital X, we got capital Y, and then we got this capital Z. Right. And this sometimes is denoted with this little ram's head. You guys can't see it. There you go. And that's because this x-axis used to be defined by pointing to Aries. And that's what that symbol there means. Okay. So for this one, we're going to have the origin at the center of the Earth. Right. And this is going to be your basic coordinate system that's going to be used to describe the orbits of satellites. Okay. So we'll be using this one later on. All right. So just remember it's centered at the origin's at the center of the Earth. Okay. All right. So there's that one. So next, let's go over the perifocal coordinate system. Okay, so now this one is going to be a two-dimensional frame of reference for an orbit. All right, so up until now we've been dealing with 3D. This one's going to be 2D. Okay? And this one is going to be centered at the focus of the orbit. Okay. So if we were to draw this, we have this. Now this is going to represent our orbital plane. So just think about, you have a satellite that's orbiting, let's say it's an elliptical orbit. This would just be that plane representing where the orbit is taking place. Okay? And we're going to have the origin at the focus. So let's say this is M1. So this will be the origin. And we're going to have an x-axis, but this is going to have little x. And then we're going to have little y. Okay? So from this point, we could measure out to this mass or satellite that's orbiting, and we could get a position vector, and you could also get a velocity vector. Okay. So this is all in that orbital plane. So that's what the perifocal coordinate system is. It's centered at the focus, which is where your major planet is, or major mass, and then you've got the satellite or orbiting object going in an orbit in the orbital plane. Alright, so now that we have that, now we're going to talk about orbital elements. So these are going to be the main elements. There's going to be 6 of them that define the size and shape of the orbit. All right. So this is what your orbital elements will be. Now we've already seen a couple of them, but most of them are going to be new. So let's cover the 2 we've already seen. So first one will be eccentricity. So we've been using that since the beginning of the class. So that's that little e. So that'll be our first one. And this one basically just tells you about the shape of the ellipse. Okay. So the larger your eccentricity is, the flatter and more elongated your orbit is. And remember, an E equal to 0, you have a circular orbit. Okay. So let's write down how elongated the ellipse is compared to a circle. Okay, so that's eccentricity. We've already used that one before. Next one, we've already seen this one before also. This is semi-major axis. That'll be little a. So we've seen that one before also. So this is essentially the sum of the periapsis distance and the apoapsis distance divided by 2. So that's another way to think of semi-major axis. So that's what you got. Okay. So this also gives you an indication of how large your orbit is. Okay, so those 2 we've seen before. So now let's get into the ones we haven't seen. All right, so the next 2, these are going to be 2 elements that define the orientation of the orbital plane. Alright, so first one's going to be inclination. And symbol for that will be little I. Alright, so this is our first new one. And we're going to draw a picture of all these in just a second. So if reading about them doesn't make sense, just when we get to the picture, hopefully that'll help. Alright, so the inclination, or symbol little I, that is going to be the vertical tilt of the ellipse with respect to the reference plane. And this is going to be measured at what's known as the ascending node. And the ascending node, that's a new term here. So the ascending node is going to be the point where the orbit goes up through the reference plane. And we'll have all of this drawn in just a second. I just want to get all the definitions done first. Okay. So that's what inclination is. So you'll be able to see it. Just basically tells you how, how high up your orbit is tilted compared to this plane, this reference plane. All right, now an important thing to remember about this angle, because this is going to be an angle, this is always going to be less than or equal to 180 degrees, and it's always going to be measured counterclockwise. And there are a few terms for some of the special cases here. So if your inclination is 0, that means you have an equatorial orbit. Okay. So you're basically right over the equator. We got direction going west to east. So that's if inclination is equal to 0. If it's equal to 90 degrees, that's going to be a polar orbit. So you're orbiting over the two poles, so the north and south pole. And then you're going to have I greater than 90 degrees, sorry. You're going to have a retrograde orbit. So for that, you would have an orbit that's going east to west. And then finally, if I is equal to exactly 180 degrees, we've got what's called an equatorial retrograde. So now you would be over the equator going from east to west. All right, so notice here when we had just the regular equatorial orbit, we were going west to east. All right, so now we've switched directions, but we're still over the equator. Okay, so that's inclination. Just deals with the tilt of the orbit. So we got 3 more of these. I don't have a lot of room here where I'm working. All right, so next one is going to be the longitude of the ascending node. And the symbol for this will be capital omega. Okay. So what this is going to be, this will be the horizontal orientation of the ascending node. And remember that ascending node, that's just where the orbit goes up through the reference plane. We'll draw it in just a second. And this is going to be measured relative to the vernal equinox direction. Okay. Okay, and this vernal equinox direction, that's just going to be that capital X that we talked about just a second ago. Okay. All right, and note here, capital omega is going to be greater than or equal to 0, whoops, not equal, and less than 360. Okay. So now we got that. Okay, so let's move this up a bit. 2 more of these. So next one we're going to have the argument of periapsis. So that's going to be the little omega symbol. Okay. So what this is going to do is this is going to define the orientation of the ellipse in the orbital plane. Okay. And this is always going to be measured in the direction of travel. From the ascending node to periapsis. All right, so that's what little omega will be. So argument of periapsis. And then finally, you guys know this one also. This will be true anomaly. So that's that new symbol. So this is going to be an angle measured in the direction of travel. From periapsis to the orbiting body. But you guys already knew that. Right, so now we got that. So those are going to be the 6 orbital elements. And I know by just reading them, it's hard to tell what those are. So let's go ahead and we're going to draw a picture and we'll have all of the things labeled. And what we're going to do with these orbital elements is we're going to get these orbital elements from position and velocity vector measurements. Okay. So as we draw this picture, we're going to kind of start the steps of figuring out how to do this conversion here. Okay. So first thing we're going to need to do is find what's known as the eccentricity vector. So that'll be labeled on this plot also. Okay, so let's draw this picture, and then I'll point out where this eccentricity vector is. Okay, so let's draw that geocentric equatorial coordinate system we had. So we got capital Z, got Y, and here's X. All right, so we have that. And now let's start labeling some things on here. All right, so here's the y-axis, and let's figure out where I want to start here. Use this. It'll make it look a little bit better. Okay, so let's put a dashed line right here. Right, so there's this dashed line. So this is going to mark where our orbit is coming up. So let's draw part of the orbit. So this is an elliptical orbit. So it looks right here. Okay. So this point right here, this is going to be your ascending node. A lot of the times that's just written as AN. And then our body is coming up this way. So it's going like in a clockwise direction. So we're coming up this way, and then right here is going to be the descending node. All right, because here we're going back down. All right. And remember the ascending node, if you look back at what you wrote down, if I can find it. Here's where we're headed. So the ascending node was where the orbit goes up through the reference plane. All right, so this dashed line here is representing the reference plane. Okay. So we're coming up at this point. So ascending node, this point we go back down. All right, so this line here is the reference plane. So let's mark that down. All right, so now we have this. Now, this origin right here, this is going to be M1. Okay, so this is going to be at the focal point of our ellipse. So we have M1 here, and then let's say we have M2, the orbiting object right here. Okay. So to get to M1, or between M1 and M2, let's draw a position vector. So let's call that R. And now, remember this is part of an ellipse here, this curved line. So now let's draw a line that represents periapsis. So this will be periapsis right here. Okay. And now let's start labeling some of these orbital elements. Okay. So first thing is we've got this reference plane, and this is our orbit. Okay, as we come up. So remember, the inclination tells you how much your orbit is tilted. All right, so I'm just going to draw this out here. So this angle right here would be I, or inclination. All right, so it just tells you how much it's tilted up. So when I get back to class on Tuesday, it'll be easier because I can flip back and forth between screens. I'll try to find y'all some better pictures of this so you can see a little bit better what that's supposed to look like. All right, but that's what inclination is. Right? Now, argument of periapsis, that is that little omega. So that is going to be measured from this dashed line up to periapsis. Okay. All right, so our definition, we said that it was going to be the angle measured in the direction of travel from the ascending node up to periapsis. So ascending node is pretty much on this line, so just draw it like that. Okay, so we've got that. And true anomaly. Remember, true anomaly goes in the direction of travel. It starts at periapsis, and then we're going to end up right there. So that'll be true anomaly. Now going back to inclination, so this right here was the tilt. So now remember we had our angular momentum vector, and that was perpendicular to the plane containing R and V, where R and V are position and velocity vectors. So if we say that's the angular momentum vector, this angle right here is also I. Okay, so now we got that. And we have our capital omega. So capital omega is the longitude of the ascending node. So that's going to start over here at the x-axis, and it's going to measure to this line. Okay. So that's your capital omega. And what else do I need to put on here? two more things. We're going to cover these in just a second. So we talked about that eccentricity vector. So we need this to get our equations that are going to take the R and V observations and convert them to orbital elements. So your eccentricity vector is going to be this vector right here. Right. So that represents the eccentricity vector. So essentially it's just a vector that's going to point towards periapsis, and the magnitude of this vector is going to have the value of the eccentricity of the orbit. And I'll write that down in just a second. Next thing I want to put on here, I think this will be the last thing we're going to put on here. This is going to be another vector, and this will be the node vector. So the node vector is just a vector that's going to point in the direction of the ascending node. Okay. So I know that's a lot of stuff there in that picture. We've got a lot of angles and all sorts of things, but after you look at it for a little while, it'll make a little bit more sense. Okay, so now we've got this. So now let's get into our equations. So these equations we're going to have, they're pretty straightforward. Your project that you're going to do is going to be to basically code up these equations and then find these 6 orbital elements. Okay. So for the rest of this video, we're going to write out the equations. Then I'll stop this video, and then in the next video, we'll have the example. Okay. I gotta get a bigger desk here. Okay, so eccentricity vector, that's what we were talking about just a second ago. So I said I'd write down what it was. So the eccentricity vector is going to be a vector that points towards periapsis. By the way, if y'all hear snoring in the background, that is my dog. I just realized she's back here behind me sleeping. Alright, so we got a vector that points towards periapsis, and like I said before, it has a magnitude equal to the orbit's eccentricity. Okay, so that's what the eccentricity vector is, which was right here. So it's just basically a vector defining that line on periapsis. Okay. Alright, so let's write down the equation. I'm not going to derive the equation, but this is what it is. So we're going to have v squared over mu minus 1 over r times the position vector r, and then we're going to subtract 1 over mu times r dotted with v times velocity vector v. All right, so this is the equation for the eccentricity vector. And remember, the magnitude of this is just the eccentricity E. All right, so now we got that. Now at periapsis, I need to stack so I can see it. All right, so at periapsis, remember if this is the edge of the orbit, we've got an R here, we've got a V here. And remember at this point, those two are going to be perpendicular. Okay, so that means that at periapsis, R dot V is equal to 0, right? Normally I would have given that as a reef pole. You guys got out of that one though. All right, so R dot V at periapsis is going to be 0 because these are perpendicular. So that means if we look at this eccentricity vector equation, that means E is going to be V squared over mu minus 1 over RP times RP, where RP is obviously this radius periapsis. Okay. and this is going to equal a constant. Okay. So you're at this one point, it's not going to change, so that's what you got. Okay. So keep this in mind, we'll come back to that in just a second. So now let's write down information about that node vector. So the node vector was that little n that we had. And I have this little caret up here at the top because n is a unit vector. And I always use that notation for unit vectors. And that unit vector points in the direction of the ascending node. Okay. So just like you saw in the picture, it just lies on that dashed line and it points towards the ascending node. So it's just a unit vector. And mathematically, we can define n as the unit vector k crossed with the angular momentum vector h. Right, so it's just that cross product. Now, when you do the cross product here, you're doing a cross with k, right? So you're going to end up with an I and a j component. So we're going to have ni times the unit vector I plus nj, it's capital J, times the unit vector j. And you're going to use these components in just a second. So again, notice this is cross product, so that means your node vector is perpendicular to the plane containing k and h. Right? Okay. So now let's get into the steps you're going to need for your project. So we're going to have position, velocity, and we're going to convert over to orbital elements. So this is how I always name my code. I always call it RV2OE. Right? I think that's just the standard notation that everybody uses for that. So we got position and velocity to orbital elements. Okay. So essentially here you're going to have a tracking station that's going to provide you with position and velocity measurements. Alright, so you have that, and those measurements are going to be provided in that geocentric equatorial coordinate system that we talked about. Okay, so they'll be in that coordinate system, and what we want to do is we want to convert that position and velocity vector over to the 6 orbital elements. So we want to find A, E, I, capital omega, little omega, and nu. Right? So once you convert over to this, you have a much better understanding of what the orbit is that that satellite or body is orbiting it. Okay, so this is going to have some pretty simple steps. You just basically are going to be plugging stuff in. Okay. And again, these are going to be the equations you need for project 1. Okay, so first let's calculate eccentricity E. Okay. So remember, we're going to be given position and velocity vectors. All right, so first thing we want to do is find the magnitude of both of those vectors. So we're going to say R is equal to the magnitude of R, V is equal to the magnitude of V. Right. Then we've got that eccentricity vector. So you're going to use that eccentricity vector to calculate the eccentricity. So we've got V squared over mu minus 1 over R times position vector minus 1 over mu times r dotted with v times v. So you're going to plug everything in, and then once you get this vector, you're going to take the magnitude of it. All right, so this will give you your eccentricity. So this is what you're wanting. And remember, in MATLAB, norm finds the magnitude. So that'll save you some time. You don't have to write out square root, sum of the squares, and all that. Okay, so now we've got eccentricity. So next thing we want to do is find semi-major axis. So we're going to calculate A. So for A, we're going to start with angular momentum. So that's H, and our H was R cross V. Okay. So once you do this cross product, you're going to get 3 components. So the I component, let's call it HI. So I'll have HI, the unit vector I, plus HJ times unit vector J plus HK, unit vector K. Right. Now the reason why we're going to start with this, if you remember, we had that parameter P equation, and that was equal to H squared over mu, and it was also equal to A times 1 minus E squared. So with this H vector, we could find the magnitude to get H here, and we already know eccentricity, right? And mu is just going to be the 3.986 times 10 to the 5th number. Okay, so that's where we're going to go for this one. So we're going to find the magnitude of H, and then you're just going to take that, plug it in here, and then solve that equation for A. So you're going to have P over 1 minus E squared. Right, so there's your equation for semi-major axis. Right. Sorry you guys keep having to watch me mess with this paper. I just don't have enough room on this desk. Okay. Okay. So next we're going to find the inclination. All right. So I is going to be the angle between unit vector K and the vector H. Right? So that was what we drew on that picture that we had. So first thing we're going to do here is we're going to start with dot product, because remember, dot product can be used to find the angle between 2 vectors, right, or 2 lines. So we're going to have H dotted with K. Let's call that H sub K. And notice you already found that right here in step 2. Okay. So H sub K has to be equal to the magnitude of H times the magnitude of K times cosine I. So this is just your basic dot product equation. Okay. And what is the magnitude of K always going to be? It's always going to be 1, right? Because that's a unit vector. So we can write HK equals H times cosine I. And then we want to find I here, so let's solve this for I. So I will be the arc cosine of H sub K over H. And this should always be less than or equal to 180. Okay, so there you have that one. So that tells you about your tilt. So it gives you inclination. All right, 3 more of these to do. Okay. So step 4 that you're going to do will be to calculate the capital omega. All right, and remember, capital omega is just the angle between I and that node vector. All right, so we have that. So let's do dot product again, because we have an angle between two lines. All right, so we got n dotted with I, and that's going to equal n, the magnitude of n, times magnitude of I, times cosine omega. And this n here, actually, that's fine. Let's do our notation. So n with no bar over it is just going to be the magnitude of n. Okay. So we know the magnitude of I has to be 1 because I is a unit vector. So that means we can say that the I component of n is going to be equal to the magnitude of n times cosine capital omega. So now just solve for capital omega. So that'll equal arc cosine of n sub I over n. So that's your equation there. Now this one you're going to have to check for the quadrant, essentially. So if n sub j is going to be less than 0, then that means our capital omega, start over here, is going to be greater than 180 degrees. So that means you need to do 360 minus capital omega to get your final value. Okay. And this n sub j here, that's just basically doing the dot product with the j unit vector and n. Okay. All right. And just so you remember this picture. So this was at capital omega. Okay. So, all right, so now we have that. So we have capital omega, and then next, let's find little omega. Okay. So little omega, that's going to be your argument of periapsis. So if we look at this picture again, our argument of periapsis is right here. All right. So that's what we're looking for. So since that little omega is the angle between n and e, so it's the node vector, that's the eccentricity vector, then again, since we have an angle between two lines, we can use dot product again. You just didn't know you'd be using dot product so much. So we're going to have n dotted with e, and then that's going to equal n times e, these are the magnitudes again, times cosine little omega. All right, so little omega then is going to be the arc cosine of n dotted with e over n e. And then let's put a box around that. Okay. Okay, so again, you want to check and see if this needs to be greater than 180 degrees. So to do that, you're going to say if the eccentricity vector dotted with a k vector is negative, so less than 0, then that means omega is greater than 180. So we'll do omega equals 360 minus omega. So in your MATLAB code, you're going to have to put, obviously you're going to put an if statement in here to check for this. And then if this is true, you need to do this calculation. Okay. All right, final thing. So we're going to calculate true anomaly. So if you look at this picture again, You got true anomaly, so that's the angle between the eccentricity vector here and this R, right? So angle between two lines again. All right, so you got the angle between those two vectors. So we'll just use the dot product. So E dotted with R is going to be equal to magnitude of E times R times cosine nu. So nu then is going to be the arc cosine of E dotted with R over E times R. Let's box that. So this one again, you need to check, see where that is. So for this one, we're going to do if R dot V is less than 0, then we're going to, so can't talk here. If R dot V is less than 0, then that means nu is greater than 180. So we're going to do nu equals 360 minus nu. All right. So again, on this one, you'll have to do an if statement in your code to check and see if you need to do the 360 minus nu. Okay, so those are going to be the 6 steps that y'all are going to code up for Project 1. You're going to have something else with Project 1 also, but this will be the first part. Okay. So that's what it looks like. So it shouldn't be too hard to code up. Should be pretty straightforward. All right. Okay, so I'm going to stop this video here and we'll pick up in the next one.